Excellent.
All right. Hello, everyone. Welcome to our third meeting of the semester. I'm Sagnik,
I'm George.
and we present the third crypto meeting, which is on block and stream ciphers.
Yep. Few announcements before we get started. So this Sunday is our joint meeting with SIGPwny. We're going to be going over cyber warfare. Learn how governments are responding to that. A lot has changed in the past 10 years, as I'm sure people in Purple Team could tell you. Definitely come out to that. Also, not listed here, but CPDC quals are this weekend. So
Yep.
cheer on our Purple Team. This is the meeting flag.
As far as CCDC goes, if you're interested, stick around. You're like from Purple Team. We're meeting directly after this.
While you guys are typing this in, like a quick show of hands, how many people were at Crypto 2? Because it has like very little to do with Crypto 2, but I'm just curious. Okay, cool. All right. This will also, we'll show this at the end of the meeting, and also these slides will be on the Discord and SIGPwny.com after the fact. So no worries if you don't type this in now. We'll go ahead and get started. So today's meeting is on, again, block and stream ciphers, so AES. So in the past, we've talked about asymmetric cryptography, RSA, Diffie-Hellman, and now we're going to be talking about AES. So I guess first things first, pseudo-randomness, this idea of we can take a little bit of randomness and stretch into a lot. So we will see this, this idea of cascading or avalanching randomness, that a tiny perturbation in your input generates a lot of perturbation in your output. It's a pretty important thing. The good news for symmetric cryptography is that these pseudo-random number generators are kind of like this is a known thing we can have. We define a PRGG that it would be difficult. We can have a cryptographically indistinguishable set of outputs that you wouldn't be able to guess the input given the output. So that's the formal definition. Do we want to linger on this, or?
Yeah, sure. A bit more of like a formal thing is that in like the theory sense, you would set up like an adversary who, let's say, he's able to like only find stuff in like polynomial time, like probabilistically, because these are again working on random numbers. So basically here, this is just this formula just represents that like if you have like some bits of like information that's already there, and if you take like a statistical amount of like measurements for like the pseudo-random generator, and you try to guess like what the bits are, the amount of times you're actually like successful over a large period of time would approach some negligible function. So that would be something like 1/2 to the n, something that like as n grows like arbitrarily large, it becomes pretty much negligible, like a very rare probability that you'll actually like guess the bits in the PRNG. And now this like mapping could be pretty much like anything. Sometimes they'll have like a lot of like XOR stages or like mixers that introduce a lot of noise. There are many other ways to like internally generate a PRNG, but this is like the formal definition. That's all.
Yeah, and again, kind of the key takeaway for AES is we are expanding a little bit amount of kind of like true randomness or initialization into a large amount of randomness. So that's the n and then the n plus s. So it's not, I guess, like fully secure, but again, this is why we introduce like an initialization vector, because we want this to be probabilistic, right? So in other areas of cryptography, you think of essentially you define some huge hash table, and then you kind of select some entry in that hash table. This is a similar idea. So again, you need it to be reproducible, because this is symmetric cryptography. So again, the difference between symmetric and asymmetric cryptography, one you have a public key and a private key, not the same thing. In an AES, you're using the same key to do both the encryption and decryption. That process is not always the same. We'll go into a little bit more detail of how encryption and decryption happen with AES. But again, it needs to be the same going in and out. We want to introduce a little bit of randomness here. So, an attacker can't just, otherwise you open yourself up to attacks.
Yeah. Think about this. If you were to use like a PRNG sometimes in like code, sometimes you could initialize it with this like little integer value called a seed. Now, if you happen to like have the seed or like the same exact number seeded into the PRNG, and then you say randomly generate one. Now, the internals of the PRNG are going to be like some deterministic algorithm. So you'll just get back the exact same random integer with the same seed. So one thing you could do is randomize the seed instead. Now, the actual like output of like that PRNG would have a little more noise introduced. So it's kind of like in that sense that you would have to introduce some other things besides just the PRNG. Yeah.
So again, your input does need to be randomized, basically. That's the takeaway. So building on top of that to actually get something that's encryption, we start off with our cryptographic key, and we're going digit by digit. If you're encrypting some plaintext of bits. So when we supply a key here, again, this is the key stream. So we have first a random initialization vector that we're feeding into G, our PRGG, with some K. This is kind of our seed slash salt. And we just kind of go byte by byte doing a simple XOR. And again, XOR is symmetric. So you just take the XOR again, get rid of the initialization vector, and you have your plain text again once by decrypting your ciphertext here, C. So this is also in practice, this is what's used for most, if you think about like your internet traffic, this is what's used for most things after the initial key transfer. So public key crypto, you're essentially establishing this shared secret with which you can do symmetric cryptography. This is a little bit more efficient, or not, I guess not a little bit, a lot more efficient. And you can stream it, which is nice. So you don't have to know all of your data ahead of time. So, a lot of data in the real world is in some sort of stream. You have a little bit of time, you encrypt that. So this is what's used in practice. And it is hard to brute force it in practice. So these are some examples of stream ciphers used in practice. Again, the ones we'll be talking about today are, it's basically just, well, we're gonna be talking about block ciphers today, but yeah.
Cha-Cha-20 in particular is pretty commonly used now, along with like, say, some sort of like associated data. If you want to like authenticate it, that's called like an AAD, authenticated encryption with associated data. So Cha-Cha-20 itself is like the stream cipher. If you have like a stream of data, you would encrypt it at like the byte level and get something that's inherently like untraceable from like the original without like the right secrets. And then you would have something called like poly 1305, which would be like the signature on top of that. So that you could say like, hey, this data is what it originally was, and it's authenticated with this. So you could actually combine a lot of these with like another authentication like code to do this. But that's like a bit more advanced. Great, Jake, you had a
what about my favorite stream cipher, AES?
AES GCM, you mean? Yeah, I kind of briefly mentioned Camera a little later. Yeah, it is there.
Okay.
It does exist.
Cool. Any other questions before we move on? I believe next is, oh, no, we're still going on RC4 here. Yeah. So any thoughts here?
I want to see everyone from Purple Team's hands up.
Yeah.
Go ahead.
Sorry, did you raise your hand? Yeah.
Yeah. Yeah, so what do you think is wrong with this? Anyone else? All right. Either way. So, let's think about like the first few bytes that are happening here. So if you look at the key schedule, every time you like take like the mod within like the first few bytes, it turns out that the original key within like say bytes 0 to like say 1 or something, does not actually get sufficiently mixed. So even if you like swap the values from like the key schedule, it turns out like the first few bytes does reveal info about the previous text because they haven't swapped with like another value that wrapped around. So using that, you could actually crack RC4. And the relevance to purple team is that Kerberos tickets use RC4. So that does make it pretty easy to crack.
Is this using like WPA1 as well, or is it
Uh,
something else?
I think so. But like if you do have like RC4 based like Kerberos tickets, you could like crack them and then Kerberos from there, which they covered in 80. Pretty nice.
Yeah, so again, as we saw there, one of the weaknesses of a stream cipher, if your key key sequence or key scheduling is short, you're leaking some information about the first few bytes. Also two-time pad. So again, reuse in crypto really kills you. Hopefully, if you write crypto 2 or crypto 1 or any crypto at all, don't be reusing things. That's not good. And if you see that in the challenges, which you definitely will, take that as a hint of somewhere to start looking. We'll go over bit flip attacks a little bit later, but also if the attacker can either know or choose the initialization vector, you can do a similar thing as what we were discussing a little bit earlier, to find some bits of the key, or find some bytes in the key rather. So again, this is why it's important that the initialization vector is truly random.
Yeah. For example, you probably don't want the initialization vector to be just all zeros. Because then like if it's XORed with stuff, which is very common in crypto, it doesn't actually do anything. Yeah.
Okay, so we'll be moving on to block ciphers. Any questions regarding stream ciphers before we move on? Cool. Yep, so this is a similar idea, but instead we're focusing on a block, like a block of fixed length instead of this stream. So we have some algorithm, some block of input, we get some block of output, and then there's a bunch of different ways, these different modes of operation, which we can use to change the inputs, and how we feed outputs into other inputs and stuff like that, which we'll talk about in just a second. But the general idea between the stream cipher and the block cipher is that this is operating on a fixed set of data, fixed size of data. So most common and most popular block cipher is AES. So I guess, is there anything beyond AES 256, or is that?
In theory, there could be, but it starts to incur a lot of like overhead, and there's like some other stuff with like the for one, like AES is very easily implemented in hardware with these like fixed key bits. So you might have to like look at like extended instruction sets if you were to go to like AES like 512 or so on.
Yeah, kind of what we were talking about earlier with streaming ciphers. They're easy to implement, and as we'll see in a minute, AES seems kind of very random in its implementation. And I encourage you. We'll have some resources at the end of this talk. But there's a set of lecture notes, and also the crypto hack module on AES is really good for seeing exactly how this mixing happens. I guess what's actually going on, and you'll think there should be a challenge, an AES challenge, published right now. But the general loop of AES, we have some set of rounds. The general thing here is we're doing a byte substitution. So we have some table, like that's literally it. You have some input, you look up an output. Then you also have, I guess I should clarify. Again, we're talking about a block. You can kind of just think of it as a matrix, like a 2D array. And these are the types of transformations we're doing. So again, substitution. Then we have shifting of rows, mixing of columns, and this round key. And again, we do multiple rounds. But again, all four of these steps are necessary to get something that's truly random. And we'll talk about why some of these are linear transformations. And that's not good if you only have linear transformations, because then it becomes easier to break. And Sagnik, we'll talk about that a little bit later.
Yep.
Right, spin on to
Modes. Yeah, no, I was gonna take.
Okay, yeah.
All right, so, well, the thing is that if you're to have like, like individual like blocks of AES like encrypted, you could actually do this in multiple different ways, as we kind of like briefly touched on earlier. So, each of these different like block, encryptions will have like, there are different like ways that the mode tells you exactly how each subsequent block is encrypted. So the algorithm itself is only good enough to encrypt like a single block of text. So if we wanted to like encrypt, say, a sequence of blocks, then we have different ways to do them. So you might have heard of some of these modes that are listed here. ECB, which is like electronic code book, I think. OFB, which is output feedback, Jake's favorite, AES counter, which is based on an incrementing counter, CBC and CFB, Cipher blockchain and then Cipher feedback. So the first one is electronic codebook, where you just independently encrypt each section of the plain text with like their own keys and nothing else. It's pretty much like the standard naive way that you would increment subsequent blocks. And those who know, settle down for a second, but what do you think is wrong with like this? Like why do you think it might be a bad idea to just like independently encrypt each block?
But it's massively parallelizable.
It's massively parallelizable.
This is great.
Yeah. Yeah. Yeah, the thing is that like every single like plain text over here in like the key is pretty much independent, and there's no like relative like mixing over here. So like, well, let's say the hypothetical that somebody was really stupid and they happened to use like the same password twice or something, and they happen to use the same username in a couple of different spaces. If they have the same key and the same like blocks of plain text going in, the ciphertext is going to be the exact same because AES is deterministic. It acts kind of like a pseudo-random function if you took all of the steps from beforehand. But because that in itself is deterministic, if you have the same plain text like parts and like similar bytes in the key, you will see some repeating sections or some repeating bytes that you could use to your advantage. So yeah, ECB is generally considered a no-go these days. So that's why we had to invent some of the later modes. A very common one that you'll see is simply like taking the output of the output of the previous block's encryption and then kind of cascading it down the line like this. So over here, we have like our initialization vector, and this would essentially be like a number used only once or a nonce. And you would put that through like the first block, and the output would keep on being like XORed. So each block has a different key inherently associated with it. So they would have a sufficient amount of noise generated from this mode. There's a couple of other modes. These are kind of like using like a key stream like before that we've decided, and this generates it from like the IV. So it'll kind of like cascade that down with like the encryption protocol. And counter mode is also there, which instead of using like the initialization vector, you'll instead have like seeded nonce at first and then increment that like counter as you go with each block. So these are some of the modes listed. And as we said before, the fact that ECB encryption kind of like does everything independently without generating enough noise, you can see clearly here, you might have like something like an original image, but if you like encrypt some of like the pixels together with like your own password with like ECB mode, does that look pretty random to you? It still looks like a penguin. I mean, it's a very nicely colored penguin, but we could still see like the general shape of what was the original image, because a lot of pixels or like data values in the original image were repeated in this case. But if we were to say use, I think this one used CBC encryption, each input into like the block kind of like cascaded down. So we have a better result of randomness here. Like now it looks like gobbledygook from that. So if we only had like ECB, it would be pretty cooked. Now, as far as like how to tell what mode's been used, this is mainly to identify if you have something that might be ECB encrypted. If you're looking for like other modes, like something that's been CFB versus CPR, that is pretty hard because if they're actually implemented correctly, it's pretty difficult to tell one pseudorandom from the other. But with ECB, it is pretty easy sometimes to tell. One thing you could do is check for repeated bytes in the encryption, especially if it's over a length of like 16. Because then you'll sometimes see like similar blocks of like text that have very little variation might have like a lot of repeated bytes that are used. And this highly suggests that there could be some sort of like pattern like ECB being done. And if there is no sign of any repeated bytes, but the ciphertext is still some multiple length of 16, now it goes down to either CBC or just ECB, but with different blocks of text. If you have a black box encryption oracle available, some CTF challenges will have this. I know Seesaw Finals did for like one of their challenges. But if you have a black box encryption oracle, then you could try sending like a byte or like something padded to like the oracle. And if you get back one byte from like the text, then that means that the encryption is happening on a byte by byte basis. So this probably means something like stream mode has been used, like output feedback or cipher feedback. But if you get 16 bytes even from sending a byte of data, now you know it has to be one of the CBC, ECB, one of those like 16 byte modes. So that's also like one way you can tell. Now, as far as like the attacks go, ECB obviously has like the most documented and easiest to implement attacks. So one of the big ones you'll see, like with that ECB penguin, is differential cryptanalysis. So if you see some sort of non-random or repeated behavior based on how plaintext bits change, and if you can trace some equivalent transformation within like the ciphertext having some repeated bytes, then it's likely that you might have valid grounds for doing a differential attack. So in the context of AES, the differentials here are basically taking XOR valued between 2 bytes. It's because of like the math of AES using what's known as a finite field in some order mod 2. But here XOR and like works the same with like addition or subtraction. So if you have like 2 known like plain text blocks with like say 16 bytes in total. So let's say P1 and P2. You can let the known XOR differentiation be like delta P here. So if you have the corresponding ciphered blocks, C1 and C2, you could have the difference be like delta C. So this kind of like goes in with like the key. And you could sometimes see here that like the difference in like the bytes here have like an equivalent exchange with like the key here. So there's like a correlation you could sometimes do with like the plain text and the outputs. And like the way you saw this was with the ECB ping. That like, yeah, the bytes were different, but the differences between them through like this method show the original structure of the image. So this could reveal certain patterns that you can then exploit within challenges. This is probably the most well-documented attack against AES, but very often, if some people decide to roll out their own crypto, which happens, you could sometimes see this thing called linear cryptanalysis. Now, the basis behind these work with affine transformations, and these are transformations upon any kind of vector of the form AX plus B. AX is generally a square invertible matrix of, say, some dimension n. And because, again, AF works on like that finite field from before, addition and XOR are basically the same thing. So you would have like the matrix operator on like some vector of bits, and you could transform that affine with like the XOR operation. So what this does is it first mixes the bits with like a linear transformation and then shifts them by like some amount by using XOR. So if A happens to be reversible, it is, as a hint, then it is possible to recover X from like that original vector. So you would just have to kind of mix everything back. You first like subtract B, which again is XOR because XOR is symmetric. You could do Y XOR B and then take the final inverse of that. And they are important as they allow for efficient mixing. But again, as you can see here, being purely linear does have its problems. So let's say somebody decided that for whatever reason, the original S box was kind of shit, and they decided to roll out their own. The S box was designed in a very specific way that has a lot of math theory behind it, but it's designed to be resistant towards both of them. Now, if you happen to disregard that and you give the S box like a predictable pattern, which you can replace bytes with, then the bit vector of like the substitution can be expressed as like that matrix formula that we said before. So there exists some bit vector B that you can like find through like testing out different values, and then some other like matrix that you could like bring into like an affine transformation. And it turns out that if the S box stage is screwed like that, every other stage that we've listed before happens to be linear. And the S box stage, like sub bytes, is the only place within AES that introduces nonlinearity. So the entire AES encryption could be basically reduced down to an affine transformation, from which you can reveal the plain text by going backwards. Yeah, this was kind of some code with like Sage Math that symbolically like reversed the shift rows and mixed columns bits. These are two steps that are linear. So thus, as you can see, I can represent them with a matrix transformation. And yeah, this is pretty easily reversible again. So as far as checking the linearity of an S box goes, it is pretty easy. You just kind of have to follow this general formula by examining like each index within the square matrix and just check if they have been like they're compatible to be like XORed with each other. So if there's like a linear pattern like this that's going through like the S box, then you basically struck gold because it's not AES anymore. It's somebody else's rolled out crypto. Yeah. That's like the advanced attacks. You'll see one of them in like the hard challenge.
Any clarifications on why? Is there a question?
Yeah.
Yeah, it's like, have you ever seen this kind of misconfigured the Xbox in the wild, or is it like more of a?
I mainly did it in like the grounds for CTFs because most people trust Rindale. But differential cryptanalysis stuff has definitely occurred in the wild. I mean, you saw with the ECB ping. Some people do kind of trust AES as inherent security. So it has happened that I forgot. I think at one point SSH did use ECB mode, but it was like a long time ago. That was pretty bad. Yeah.
I mean, it was developed at some point, so
Yeah.
it's probably used. But again, just to clarify, because it's not like super relevant to the attacks we're gonna talk about right now, but kind of on the same page on if all your encryption is doing an affine transformation, that's bad because computers are really good at affine transformations. We're all on the same page here. So make sure your sub-byte step is doing the right thing. And again, in practice, this comes down to just not choosing your own SBox. Okay, so we'll start talking about bit flip attacks. So this is going back to CBC, and I think we have OFB mode here. So again, I don't think I have my pointer here, but the idea being we're feeding the output of one block into the input of another block here. So in this case, we have the ciphertext, and that's getting fed in here to create or as part of the encryption of the next block of ciphertext. So if an attacker knows something about the positions of the ciphertext, I think the example we give here is like a permission bit on a file or something. You are able to deterministically flip a bit in the next block, right? Because again, all you're doing here is XOR, so this has the same effect as if you were just XORing a bit in the plaintext or flipping a bit in the plaintext. So that is what this allows you to do in practice. So you don't need to be able to break the cipher at all. It's just a matter of flipping a bit. And so if you know you don't have permissions, and you know if I flip this bit, I have root. Well, there you go. And then this is the exact same idea as we just discussed. And I'll kind of go back and forth between these. Apologize that these are not on the same slide, but just so we get the understand the difference between CBC and OFB. Again, our XORing with the plaintext then happens after we're doing our block cipher. And here again, the output is just fed directly from the output of one block cipher to the input of the other. So here again, the situation is a little bit different. When we flip a bit, we flip it in the same block. And when we're changing this, we're not actually changing the output or the input to the next block, right? Because the ciphertext here is not getting fed into the input of this block cipher. So this bit flip is effectively undetectable. I mean, not in actuality. Like there are modes like a modification of OFB which avoids this problem, and you can say, oh, hey, a bit has been flipped, something's not right. And again, this is why it's important that you also have some sort of like a message authentication to make sure your message has been tampered with in transit. Yeah, and then this is the alternate CFB mode, which we do not have a picture of, but you can kind of take my word for it.
You could look it up. Most of these diagrams are out there.
There's a good comparison of 6 different modes of AES encryption on Wikipedia. Just like that's exactly where these diagrams are from, all side by side. Do you want to talk about Pen Oracle or? Yeah. So again, when you build off the kind of the same idea of bit flip attack is this pattern Oracle. So Sagnik was talking about a little bit earlier. I guess a kind of oracle of finding out what type of AES what mode of AES you're in. This is a similar idea where you have some oracle, which I mean, in practice, you'll probably construct yourself, but you have a server, it says, give me plain text, I'll give you ciphertext back. And you're able to find out something about what padding that will accept. So again, you can basically just sweep or scan the available things and to kind of just guess what the correct or acceptable padding would be. So here's the attack kind of in practice. Now you have C1, C2, and you flip a byte. You send us some oracle, which in practice in a challenge you may have to do a little bit of conversion yourself, but the idea is basically the same. And you again are kind of rinsing and repeating until your padding is correct. The oracle has returned that your padding is correct. Now you have one byte, and you can use that byte to get another byte, and so on and so forth. So that's kind of the idea of the pattern oracle attack. But it is basically educated guessing one at a time. But that's the vulnerability here.
Yeah. The really nice thing about the padding oracle attack is that based on like the way it's structured, if you use that like insecure padding, which generally like if your like block ends like say 3 bytes before the 16-byte boundary, you'd basically pad it with x3, 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 like 3 instances of that like byte. So one thing you could do is that if you like keep on brute forcing like possible bytes to like check, if your Oracle suddenly returns, hey, this is valid padding if you put this byte in, then you can literally use that information to your advantage to like figure out the previous byte and then the next byte and then the next byte and so on and so forth. That's kind of the idea behind this side channel. It's rather hard to explain in words. So I think Wikipedia does have a nice GIF of going through the actual like brute force. And it is efficient because at worst, you'll only have to check 256-byte values and like within like a 16-byte block. So it is finite and pretty easily computable for padding Oracle. Ronan, you had a question?
Well, I guess I do have a question. I raised my hands, but
You did.
I see how this would let you get the last non-zero byte. How would you get the one before that? I don't fully understand.
You would get it through basically this has to do with like the actual like value of the padding. So like for example, if you had like x2 x2 or something, then like you'd have to like mess with like those 2 bytes until they get x2 x2. Yeah.
Is that bigger image of this?
There's a bigger one.
Yeah, it's like right there. Yeah.
Yeah, it's not, we unfortunately, we do not have a great visualization. If you go to the, we'll have the link both at the end of the slide, but you can also Google it now. The crypto hack AES module, I think it's just called, has a really good, both interactive challenge, which you can get points for on Pwny CTF, but also visualizations and explanations on all these attacks, what they're doing. But I think it's especially helpful for Python Oracle because it's a little bit tricky to explain in this format.
Yeah. I think this is probably like the best idea behind this. So you would kind of like independently repeat this for like each byte going on. Kind of. I think there is like a better GIF for this because I remember seeing it. I should have probably added this to the slide beforehand, but you'd basically like continuously like check values until you like reach that.
Do you want me to pull this up on?
Yeah. Please pull it up.
Okay.
Just padded Oracle GIF. No.
I'm going on images.
Search up GIF.
Right here?
Yeah, this one. Yeah, so as you could see here, sometimes like a good thing you could do is like check your IV sometimes, and then use that like padding to find out like which IV zeroes out the previous byte. And then you could use that for the next step. Then check like which padding or like plain text would read to like the next one. So in this case, this uses the initialization vector to do it. But yeah, the general idea is that you would continuously like change values through like the previous block to influence like whatever goes to like the next block here. In this case, this is like ground zero because you start with like the IV, but you could even start from like the previous block. Yeah.
Yeah. Again, it might be helpful to think of this. Again, we showed you ECB. Don't do ECB, it's bad, but this is somewhat kind of like that. Insofar as you want to change the input into one block in some way, some deterministic way that you know, in order to mess with the output, find some pattern, and then you can kind of build upon that iteratively. That's the general idea. Okay. We will go back to the slides.
There are some tools that do it, if you have like access to like, say, a web oracle or things like that. But then again, it's not very difficult, like in particular to write like your own pattern oracle like code. I mean, a good example of that could be like this Python script here that does it. But if you have access to like some like web input that you could fuzz, probably you could use like Padbuster or Bletchley. Yeah, so there are tools to like help automate it.
All right. And again, this is just more of a general thing, not just for pattern oracles, but for AES and crypto in general. Crypto hack, which you mentioned before. Also, there's a set of lecture notes from a professor at Purdue, which are, I shouldn't say surprisingly good. That makes it seem like I just like the lecture notes for some reason. I'll just say they're good. Above my bar for lecture notes, I guess. I guess that's what I mean by surprisingly good. A lot of stuff is guess the paper, I guess a little bit, when it comes to CTF challenges specifically, a little bit less in block ciphers, just because of the nature of it. Generally, you see that more with some ECC and advanced stuff that we'll be talking about at Crypto 4, so stay tuned for that. And as always, SageMath, PyCryptoDome, Crypto Stack Exchange, Google, and your number one and two best friends in the whole wide world, your pen and pencil, or sorry, your pen and paper. Paper comes in at a close number 3.
Yeah.
All right. So are there any more questions before we move on? We'll let you guys to do some challenges. But any clarifying questions here while we're up here? We'll also have time to answer questions after the fact. Cool.
Yeah.
Cool.
We have a couple of challenges up, like varying in difficulty. So feel free to attempt those. There's a lot of similar stuff. Anyways, again, a rehash of like the next meetings. This Sunday we'll have the Cyber Warfare meeting, which is going to be really cool. Stay tuned. Next Thursday we're going to do Pwn again with
me.
Rob.
Yes.
With George.
Rob, we're doing Rob first this time. Yippee.
Yeah.
And then next Sunday, Nikhil is here. Do you know what seminar it's going to be? Well, it's TBD. As you can hear, it's TBD. Yeah. So here's the flag again. We'll go around. If there's any questions. Yeah.
That's all.
Challenges are up under crypto and, or sorry, stream and block ciphers.